Hello everyone, how's it going? Can you hear me okay? Is the audio doing fine? Sound alright? Okay, excellent. Yeah, probably give it a few minutes, see if people sort of roll in the standard. Um, yeah. Hello, Narf. Glad to see you here. Alrighty, I think I might go ahead and get started. Glad to see people here. Hope everyone's having a good weekend, all that good stuff. Um, yeah, this one should hopefully be interesting. This one's going to be a little more general. So last time we did this, we sort of just cranked through a few problems, right? We took this Hamiltonian formalism and we applied it to some physical systems and just sort of derived the dynamics of those systems. So today the hope is to sort of maybe get some more, not necessarily machinery, but gather together some more of the fundamentals that apply to pretty much any physical system. So the way that we will do that is by talking about something known as phase space. And so the nice thing about phase space is that you can use it to sort of simultaneously describe lots of systems at the same time. So you don't have to necessarily specify to, okay, I have a harmonic oscillator with these specific initial conditions, and how does that evolve? Instead, you can really look at the evolution of a harmonic oscillator for any initial conditions. which is actually the very first thing that we're going to look at, and look at its evolution through phase space. Now, these ideas of phase space, and particularly the next point, which is this Liouville's theorem, these are particularly important concepts in statistical physics. So they don't show up necessarily as much in your standard run-of-the-mill classical mechanics, just because in classical mechanics we tend to be looking at things sort of exactly. So looking at a spread of systems isn't necessarily as helpful as in statistical mechanics, where you have sort of a probability distribution of the type or of the starting points that you could have, for example. So that's sort of just to have something to keep in mind while we're talking about this, and why this talk of phase space and everything might be important. And then, so after we talk about that, we're going to show Liouville's theorem, and then we're sort of going to connect it all into a very interesting case of, well, as I'm sure people could guess, the double pendulum, the infamous double pendulum, and see an example of what's known as chaos in physics and math, and we'll use this language of phase space and Liouville's theorem and all of this in order to really pinpoint what we mean by a chaotic system. And this is just sort of to give a specific example of where this stuff might be useful, but of course it's useful in plenty of other contexts as well. So with that, we'll go ahead and get started. Of course, as always, feel free to ask questions in the chat. Always trying to keep an eye on it. And again, as always, I'll be pausing here and there to see if people have any questions as we go. But so to get started, we should probably talk about what we mean when we talk about phase space. So when we do this Hamiltonian formalism of classical mechanics, we've seen that we treat our dynamical variables. Wow, if I can spell. Dynamical variables, q sub I, so these are our coordinates, and p sub I, which are our momenta, as independent. So these are all completely independent variables that they become coupled through Hamilton's equations. So we assume that all of these are completely separate. They're all independent, but we allow them to sort of come together and talk to each other by means of Hamilton's equations. And so this is going to determine our evolution of the system, is the Hamilton's equations. So the idea of phase space is that, so say I have, we're going to say we have n q sub i's and n p sub i's. Then we are going to define phase space as the space which is essentially whose axes are made up of all of our independent coordinates. So all of the q sub i's and all of the p sub i's. So our phase space is the space made up, I guess I'll say, this is the 2n dimensional space made up made of all of the q's and p's. So 2 n-dimensional because we have n q's and n p's, and if we give one axis to each of the q's and one axis to each of the p's, we're going to end up with 2 n axes. So this is going to be a 2 n-dimensional space. So as we'll see, this can be very helpful for sort of even just simply picturing what's going on in a system. Phase space can be very helpful. The unfortunate thing about it is plots of phase space, just call it PS, are difficult for n greater than 1. So if we have more than 1 degree of freedom, obviously you can see, so even if we just have a single particle which is allowed to move in 2 dimensions, right? So this isn't even a physical system where a particle can move in 3 dimensions. We already have 4 dimensions. Our phase space is already 4-dimensional, right? We have a coordinate in the x direction, a coordinate in the y direction, and then a momentum in the x direction, momentum in the y direction. So obviously it's going to be very difficult to draw plots in phase space for any sort of complicated system, but as we'll see later on, we can still, we can do it just fine for a 1-dimensional system, or we can sort of look at just like cross sections in phase space if we want to plot them. But so this is something to sort of keep in mind of, when you have more degrees of freedom and you're looking at phase space plot, you're not looking at the full phase space plot because it's, very hard to draw something in 4 dimensions. Okay, so with that said, we're going to say that we can designate a point in phase space. So a point in phase space is given by, I'm going to put it in quotes, a vector, which I'll call z sub I. And the way that we'll define z sub I is z sub I is equal to q sub I. So this is a 2n-dimensional vector. And then z sub I plus n is equal to p sub I. So here I is equal to 1 to all the way up to n. So for example, if we have 2 degrees of freedom, say q1 and q2, then my z vector, again, sort of in quotes, is going to be q1, q2, p1, p2. Like that, where we sort of split up the vector into q's and p's. Now, I put vector in quotes. This is actually somewhat of a subtle point, but it's important to mention, I think. This isn't a real vector because the q's and the p's transform differently. So if I get this correct, I do believe that if q sub I goes to q sub I prime, q sub L, this I can usually write as, oh boy, I think in this way, EQJ, QJ, and then p sub I is going to transform, I believe, in the opposite way. I will admit I do always get these backwards, so if I'm messing this up, feel free to let me know. But I think this is qj dq prime I p sub j. And in principle, if this were a real vector, all of its components would transform the same way. It's a subtle point, but it's worth mentioning. So keep in mind, this isn't a true vector, but we're going to treat it as a sort of quote unquote vector, nonetheless, because it still points to a point in phase space. Okay, so with that said, erase this guy. It's sort of partially a way of shortening a lot of our notation, because now instead of talking about all of the q sub I dots and the p sub I dots, we can just talk about the evolution of z. And the evolution of z is, of course, just going to be given by the Hamilton's equations of motion. So it's partially sort of notational, but it's useful nonetheless. So yeah, so I mean, I can just write this out again, where this is going to be z sub I is going to be dh d, well, this is going to be z sub I plus n, and then z dot I plus n equal to minus dh dz sub I. Again, for I equals 1 to up to n. Okay. Okay, so this is a set of 2n first order differential equations, which means that there is a unique solution to this set of differential equations for each given, I'll call it z, I don't know, call it z sub n 0. So this is my boundary condition. Where now here I'm assuming that n runs all the way to 2n. So all of my z's need some boundary condition. Another way of saying it is each of my first order differential equations needs some boundary condition. So I need 2n boundary conditions. And once I specify that, I have a unique solution, right? This is just a property of differential equations, right? Specify my boundary conditions for these first order differential equations, I'm guaranteed a unique solution. So this is actually an important point. Because, well, so now all I have to do is give my Hamiltonian, get my differential equations, specify my boundary conditions, and I have the complete evolution of the system for any time, right? Once I specify this guy, I now know the state of the system at any other time exactly. This isn't something really new. This is what we've been doing the entire time with classical mechanics, but I want to reiterate that that point just a bit more, with a bit more emphasis. So an important consequence of this is that two paths in phase space will never cross. I'm actually going to underline this never quite a bit. So no two lines in phase space. If I track an orbit of a of the system in phase space, no two of those orbits will ever cross, right? So if I draw a phase space diagram, we'll make it 1 degree of freedom, so that I have Q here and P here. If I were to have, I don't know, some system A, right? A with initial conditions, we'll call it Z0A. And then I look at maybe some other system, which I'll call B. And these have some initial conditions, Z0B. So Z0A and Z0B are these initial points here, right? So these are Z0A and Z0B. So now I can just use Hamilton's equations, and I'll get some evolution through phase space. I don't know, it might look wild, wacky, however it might look. The point is that no two of these paths can ever cross each other. And this is actually fairly simple to see why. So, we'll consider the contrary. We'll consider what happens if I have, say, some system here that goes like this, and then another system which does cross over the first one. Okay? So now I need a different color. How about blue? Now we'll consider a third system, which I'll call C. C with initial condition Z0C, where its initial condition is the crossing point in phase space. So now remember that we know for a fact that every single initial condition corresponds to a unique path through phase space. But now I have two possible paths that the C could take, right? It could go along either one of these. I don't know which one it is. So I've now, I've essentially spoiled the uniqueness, which we know can't happen. We know that our set of differential equations for a given initial condition must have a unique solution. And so we see that paths in phase space can never cross. Okay, this is actually pretty important, right? This is a pretty important result. It's interesting. And just to sort of give an example of it, I want to look at one of our favorite systems to look at, period, which is the harmonic oscillator. Okay, so the harmonic oscillator has a Hamiltonian. We're going to specify to one dimension so that we can actually draw these plots fully. K over 2 x squared. This is our Hamiltonian for the harmonic oscillator. We can write down Hamilton's equations of motion, dH dp, which is of course just p over m. We have p dot is equal to minus dH dx, but p dot using this equation we also know is equal to mx double dot, and taking this derivative we get this is minus ax. So this is our equation of motion for x, and then we can use that to find p using this equation of motion. This is pretty straightforward. We've solved this system many, many times by now, so we should know that this is just a cosine omega t plus b sine omega t. And then I can take a derivative, and I find that my momentum is given by minus am omega sine omega t plus b m omega cosine omega t, where here omega is defined to be square root of k over m. So at this point, I have to specify initial conditions, right? Or boundary conditions, whichever we want. And we'll choose those to be at time t equals 0. Our position is just at x naught. And our momentum at t equals 0 we'll just call p naught. Sort of just plugging these in, we can solve for coefficients a and b. And we find something which looks like this, plus p naught over m omega sine omega t, and then p of t is equal to minus x naught m omega sine omega t plus p naught cosine omega t. Okay. Excellent. So, yeah, if you have any questions, I can go over things a little more slowly, and okay. So, a question, but aren't many physical systems going to end up in indistinguishable final states regardless of the initial values? Well, what we've just said is they can't, right? They at any given point in phase space, these cannot end up in physically identical final states, right? If I specify an initial condition, the evolution is unique. Two systems can get very, very close to each other. They can be very, very close, but they are going to be distinct, right? Unless I start them with the same initial conditions. And actually, when we talk about chaos, we'll actually see the opposite happen. We'll see two systems which start in almost identical initial states. These are going to evolve to be vastly different. That's sort of the whole idea of chaos. And actually, probably more outside of very controlled environments, a lot of systems are going to be chaotic. So it's probably going to end up being more of the opposite, where if I start two physical systems very, very close together, they'll end up completely diverging away from each other and look completely different. I think that's what you're asking. If not, feel free to clarify. Okay, so Narf's response. I like this response. So a ball rolls down a hill and bumps into a wall. It will come to rest at the wall no matter how high of the hill I started at. Am I just not considering all of the phase space? And the next comment is exactly correct. You're not considering everything that's happening in the wall. The wall, you're going to have a whole bunch of complicated dynamics happening. And most importantly, if you neglect everything that's happening in the wall, you're now considering a non-conservative system, in which case most of what we've been talking about with Hamiltonian mechanics has been only for conservative systems. So if I want to be able to describe that, I absolutely have to consider all of the complicated dynamics happening in the wall. And of course, if I drop a ball from, 10 meters versus 20 meters, the what happens on the wall is going to look very different, right? That's an excellent question. It just means that, like you said, you're not considering your full phase space. And again, what we'll see later on when we look at the double pendulum, we're just going to look at a cross-section, it will look like paths are crossing in phase space, but it's because we aren't considering the full phase space where things can move in other dimensions, so that this crossing isn't actually happening. But yeah, great questions. Yeah. Yeah, the wall phase space is going to be gigantic. It's going to be huge. Yeah, you're exactly right. And this is something that happens a lot in statistical mechanics, because that's the sort of thing that statistical mechanics tries to do, is study these systems with huge numbers of degrees of freedom, and so you just get massive phase spaces in these. But that's not we're not gonna look at any of those today, so fear not. Our phase spaces are gonna stay pretty small, relatively. But okay. So back to our harmonic oscillator. We have these two equations, and if you sort of work it out, maybe if you stare at it long enough, whatever, you might be inspired. But something that you'll find is that x of t squared plus p of t squared over m squared omega squared. This ends up, I mean, if you want me to do it all out, I can do it. It's just some algebra and trigonometry. But this ends up just being x0 squared plus p0 squared over m squared omega squared, which is equal to a constant, which, I don't know, I'll just call alpha. So my equation for the evolution through phase space is going to look something like this: m squared omega squared alpha equals 1. But as we saw last time, this is the exact equation for an ellipse, right? An ellipse centered on the origin with semi-major and semi-minor axes, alpha and m omega, or m squared omega squared alpha, depending on which one is bigger. Right, because if I want to plot an ellipse, I have something, my equation is something like this, where t just sort of determines where I'm at on the ellipse. So I mean, basically, this is pretty simple, but you can see that if I plot this out in phase space, if I do x of t and p of t, and I start a particle, I don't know, at some arbitrary point in phase space, it's going to evolve. If I can draw this correctly, if we pretend that that's an ellipse, it's going to evolve around this ellipse this way, right? It's going to go around in a circle, or in an ellipse, just sort of looping back around this ellipse. But now, what's interesting is that if I change, so notice that both the semi-major and semi-minor axes are proportional to this same constant. So say I consider a different system with different initial conditions. So I'll say I have one system which is x0, p0, and then I have another system which is x0 prime, p0 prime. So that, I don't know, I'll say alpha prime is this guy x0 prime squared plus p0 prime squared over m squared omega squared. So now we see, again, this is just sort of another restatement of no two paths can ever cross in phase space. So say alpha prime is bigger than alpha. In this case, then we end up that both the semi-minor and the semi-major axes are bigger, which means that I'll end up with an ellipse that is, say, out here now. Because both the semi-major and the semi-minor axes are bigger, the ellipse as a whole has to be bigger, right? If maybe the semi-minor axis was bigger, but the semi-major was smaller, then or probably the other way around, I might end up with something like this, which we know we can't have. But we've just seen sort of another restatement of this fact that no two paths can cross. That's sort of a concrete example of how this no crossing can work, which is pretty cool. And of course, you can see the same thing happens for alpha prime less than alpha as well, except in that case, you're going to get something like this. The branch of physics that I am talking about right now, just to answer a question in chat, it's just classical mechanics, but specifically done using Hamilton's approach. So Hamiltonian mechanics is usually what it's called. And so specifically, we're looking at phase space evolution in Hamiltonian mechanics. Okay, so this is cool. This is interesting. But we might try to take this one step further, even. And instead of just one point at a time, maybe we want to plot an entire blob in phase space, right? So maybe we want to plot something which looks like this, and see how this entire blob in phase space evolves, instead of just a single point. Well, it turns out we can actually do that. And to sort of demonstrate it, we'll go with an even simpler system. So just consider a free particle. So free particle in one dimension. In this case, there's going to be no potential energy because it's just a free particle, so it's just going to be moving along unimpeded, in which case the Hamiltonian is just p squared over 2m. Hamilton's equations are particularly simple. We just find that x dot is again p over m, and then p dot is, of course, mx double dot from this first equation, And then from Hamilton's equation, there's no dependence on x here, so this is just 0. If we again say that x of 0 is equal to x naught, and p of 0 equals p naught, then this system of equations is fairly straightforward to solve. And we just get p0 over m t plus x naught. And then p of t is p naught, which of course we know because momentum is conserved in this case. Okay, so this is interesting because we can sort of see, if I draw a plot of the phase space here, we can sort of think about how things are flowing in phase space. Almost think of phase space as almost having fluids in it. So in particular, we can see that anything on the for any given point p0, the system will always stay at that height, right? So if I draw a point, say here, the height of this point is never going to change. It's never going to do anything like that. It's always going to just evolve something like that. Okay? So then we can also see by looking at the other equation that how much it moves in the x direction is determined by this height p. Right? The higher we go in p, the faster it's going to be moving, and the more in the positive direction it's moving. The lower we go in the p-axis, the more negative it's going to be moving. So overall, we're going to end up with some flow, which is going to look something like this. Right? We get what we might call a shearing flow. Where the amount that it's changing is going to increase as we go either up or down the axis, and particularly when we're sitting on the x-axis, nothing's ever going to change. So what we might expect to happen is if we have some blob in this phase space, right? So say we start with some blob which looks like this. The top is going to get pulled this way fairly hard, and then as we go closer and closer to the x-axis, that pull is going to be less and less. And then once we're sitting on the x-axis, the points there shouldn't change. And then the same thing should happen here. And we should get some sort of stretching and squeezing happening on this blob in phase space. So this is easy enough to do. And when we do it, we get something that looks like this. So as we might expect, the farther up we go in the p-axis, the more it's going to move, sort of the faster it's going to be changing. And as we get more negative, the faster in the negative direction it's going to be changing. And so we're going to get this shearing of the shape and sort of stretch and squeeze it in phase space. So this is sort of one of these useful things that we can do in phase space. We can look at the evolution of a system as a whole, right? And you can already see how this is going to be useful in something like statistical physics, right? If I know my initial state of the system is somewhere within this little blob, right? This initial circle that I drew, I know it's somewhere in there. I don't know exactly where, but it might be described by some probability distribution, whatever. I can now track at a later time, well, where else could that be? In principle. And we'll actually see very shortly that that's exactly what I can do. That's sort of what this Liouville's theorem is actually saying. But with this little animation up, I'll take a break, see if people have some questions. Take a sip of water, and then we're going to get into this Liouville's theorem. Yeah, so Narf is mentioning the three blue, one brown video. Of course, I'm sure many people watching this has seen 3 blue, 1 brown, an excellent content creator. And yes, that's he talks about this phase space, this fluid analogy in phase space, and we'll actually see again very shortly what this Liouville's theorem is saying is that not only, so again it ends up being that not only can we treat a blob like this in phase space as a fluid, but we can treat it as an incompressible fluid, which is very cool. It's a very powerful thing to be able to do. Sort of, again, spoiling the sort of end result of Liouville's theorem. But yes, basically everything 3 blue, 1 brown puts out is excellent channel. No, the fluid analogy is a very common one because it makes a lot of sense to do. But okay, so I guess I'll go ahead and move on. I'll keep my eye out if there's any sort of burning questions in the chat. Fluid flow explains everything except actual fluid flow. That's pretty good. That's pretty funny. Okay, so so I made this statement about, if we start with some blob like this and it evolves into some new blob, and we say in, say, a statistical setting, I want to say that, okay, those states have now evolved to this new blob. So that's going to be my new distribution that I can look at. How do I know that those are actually the same points, right? How do I know that this initial volume is going to end up containing everything that later volume contains, and vice versa? So we want to actually look at how this volume as a whole is going to evolve. So we can do that, and we're going to try to do this in a fairly general way. But we're gonna stick to Cartesian coordinates for this. So we're gonna stick to Cartesian. But the results hold in any set of coordinates. There's just some extra complications that show up, but the results still will be the same. Okay, so here's sort of the limitation of talking about phase space, is that it becomes very hard to draw these pictures, but say I have some volume in phase space, right? I'm going to draw it as a three-dimensional volume, but of course in phase space, we're never going to have a odd dimensional volume, but sort of bear with me on this. Okay, so this volume, we'll say, is at some time t. We'll call it a volume V at time t naught. It's going to evolve, and I'll draw its evolution in green. So this this is how the volume's going to look. We'll say after some time, t naught plus delta t, and we'll call this V plus delta V, right? It's the original volume plus some extra stuff, which we'll call delta V. So how can we I guess, measure this evolution? Well, we can do it by looking at some small piece of V, which I'll call ds. And don't worry, I'm gonna blow up this picture in a second to get a better look. Now this small section of the original volume V, I mean, we can track its evolution after time t, and it's going to evolve to some, I don't know, maybe we call it ds prime on V plus delta V. And we can track its evolution, and let's see how good of a artist I can be for this. But so it's going to evolve in some way like this. And actually, I'm going to sort of shuffle things around, move this over here, and I'm going to blow this up. So here I have some piece of V, and here I'm going to have some piece of V plus delta V. And so just maybe for simplicity, whatever it may be, I'll just draw this as a circle here on V, and this is going to be ds. And maybe it evolves to here after some time. And actually, I'm going to just erase the ds. So I can track this by drawing some, it's going to look like a cylinder, but it doesn't necessarily have to be a cylinder, but just to sort of give you the idea. Now, if ds is very small, we can expect that the bottom, or the part on V and the part not on V, or on V plus delta V, are going to be pretty much the same size. Specifically, we're going to make ds infinitesimal, so it's going to be the same size either way. So I'm going to end up with some shape. You know, it might be sheared in some weird way, whatever. But didn't do a great job of drawing that. We're going to get some shape which looks like this. I'm going to blow this up a bit. This is the shape that we care about. So the idea is that we take all of these little tiny ds's, right? We take all of these ds's, and we take all of them and we add all of these little pieces up from the original V. Now we know that two paths can't cross in phase space, so we know that none of these ds's are going to cross either, which means that if we sum up all of these little pieces, all of these little ds's on the original volume V, we should be able to, so we take these volumes. Sorry, let me start over. So each one of these ds's is going to produce a volume, right? This volume I'll call delta V ds. If we were to add up every single one of these volumes, since none of the ds's cross, that will give me the all of the little tiny pieces of volume that make up this delta V. Right? You can see that if I draw some blob here, right, I get some piece there, some piece here, which connects down to here, so on and so forth. So I'm basically building this intermediate volume delta V one little piece at a time. So if I were to find these delta V's and I sum up all of the delta V from each ds, that should give me my total delta V. Hopefully that makes sense. If it's confusing, then I can go through it a little slower, but okay, so what's this volume gonna be, right? We want to find us something for this, right? We want to find an expression for the delta V ds. Well, we know that it's gonna, this shape, we just have to take base times the height, right? That's just the volume of the shape. Because the actual face, the faces don't change, right? We've already said that since this is an infinitesimal, the area of the faces we're assuming isn't going to change. So then we just have to find the height. Well, the height of this thing is going to be given by this vector here, dotted with whatever this normal vector is, n hat. Okay? So I can describe this first vector that I drew by, this is getting a little cramped. I think I'm gonna erase this intermediate drawing. So remember, this lives in phase space, right? N-dimensional phase space. I can describe this first point by some phase space vector, which I'll call zi, zi0. And if I didn't draw this super perpendicular parallel, I can draw a second vector. Sorry if it's sort of overlapping. I'm going to do it in a different color. So I can draw a second vector like this, which I'll call z1i. So then this height, so this vector here, which I will draw over in green. So this vector here is just going to be the difference between these two vectors, right? So I'll call this delta zi. So this is how much this z vector changes. And that's z1i minus z0i. Okay, so I want to take this delta z vector. I want to take only the piece of it which is given by, which gives the height, which is the piece which is perpendicular to the original face. which is given, which I can find by dotting this delta z vector with the n hat vector, with the normal vector. And that gives me the piece of delta v, which is perpendicular to this original surface. So sort of tying this all together, this is given by ds, which is just the area of each of these little slices as we go up, times the height, which is n sub I. So remember, n is our normal vector to the surface, delta zi. Okay? Yeah, sorry, I'm not the best artist here. So hopefully the drawing sort of makes some sense. Argument makes sense. Again, if you have questions, please feel free to let me know, and I can go through it again. Okay. So now we're going to assume that delta t is small. Assume delta t is small with the intention being that we're going to end up taking delta t to 0 to find the instantaneous rate of change of the volume. That's what we want. So if delta t is small, then my delta zi, well, I mean, I can say that my z1 I, I'll just say is zi at t plus delta t, which means I can expand in delta t, which just gives me zi of t plus delta t times z dot I t. So you can see that the change in this vector z, right? So we're only concerned about the change here, is this. So this is going to give me delta zi, assuming that delta t is small. So I can just substitute that back in, and I find this, ds n sub I z dot sub I delta t. Okay, so now I'm going to sum over all of these pieces. So I'm going to sum over all of these ds pieces, which make up the surface of our original volume. And that, of course, is going to give me my total delta v. So this total change in volume is going to be given by the integral, right? We're doing a continuous, whoops, not over ds, over just the surface. We're doing a continuous sum, right? Because we're shrinking these ds's down to infinitesimals of just this guy, I delta t. Now delta t is a constant, so I can move it back and forth and out of the integral. And in fact, I will divide both sides by this delta t. So I get delta v over delta t is this surface integral n sub I z, oops, I dot. And actually, I mean, in principle, I should be including some order delta t squared terms, but since I'm taking the limit as delta t goes to 0, I'm just going to do that here. These higher order terms are all going to drop out, and I'm going to be left with the time rate of change of this guy. So this is how my volume changes. My volume in phase space changes in some small amount of time, right? It's given by the sum over all of these surfaces of essentially the pieces of z dot. So how my phase space vectors are changing at each point on the surface. Okay. Yeah, so since it's the normal dotted with z dot, this is essentially describing the total amount of z dot I, which is perpendicular to the surface S of our volume V. There is a word for this. This is the flux of zi dot through S. So when you hear flux, that just means the total amount of something which is going through the surface, not parallel to the surface, but the amount that's going through it, which means the piece which is perpendicular. And that's all we're finding here, right? We're just finding the flux of z dot I through the surface S. Okay, I think I'll take a quick pause here because I know that was probably confusing, and I want to see if people have some questions on it that I can clarify. So feel free to ask anything, chat. Yeah, hopefully it wasn't too painful. Okay, well, I'm not seeing anything. Okay, I'm not seeing anything, which that's good. I'm glad. Of course, if you do have any questions, don't be afraid to ask them. But so we can go ahead and move on. So, okay, so our rate of change of the volume is given by the total flux through this surface, the total phase space flux through the surface, right? So however much our phase space vector field is changing through this surface of the volume. This is fine, but it's also not very enlightening. So to get a more perhaps useful picture of what's going on, we're going to look at taking some initial volume, draw bigger. We're going to split it up. We'll split it up first, just sort of roughly in half. And we're going to call this surface sigma. Okay, so now say we have this z dot vector. We have some of it, it's going out like this. Maybe in some other places it's coming in, going out, whatever it may be. whatever this may look like, there's going to be some total flux, which I'm going to call phi. Phi is equal to the flux. And in particular, the total flux I'll call phi total. Okay? So what happens when I look at, if I split this thing up, right? I'm going to split this up into volume 1 and volume 2. So, say part of this z dot field is flowing through this this surface sigma, right? So let's say we have something like this happening. It's flowing out of V1 into V2. Well, we'll say that it's, whatever pieces are perpendicular are the net effect is that you get something flowing out of V1 and into V2 along this surface. Well, then you see that if I define it so that, okay, so maybe say I have some normal vector pointing this way. This is the normal vector of the surface sigma. So phi out of V1, this is going to be some positive value, which I'll call just plus lowercase phi. But according to V2, the normal vector is going to be pointed in the opposite direction, right? So if I define the normal vector to always be pointed out of my volume, so I'll call this 1, then my normal vector for V2 is going to be pointed in the opposite direction. So that phi of V2 is equal to minus phi. It's the same thing, right? The surface didn't change, so the total amount of the vector field going through the surface isn't going to change. It's just the directionality is changing. Well, and so each of these, I'll actually just call this by sigma, just the piece which is going through sigma. So, but this makes sense, right? This intuitively, this is sort of like one of those duh moments, right? Anything that flows out of V1 through sigma is going to flow into V2, right? That's all this is saying. So I can essentially write that phi through sigma, the flux through sigma out of V1 is equal to minus the flux through sigma out of V2. Anything that flows out of V1 has to flow into V2. But so then, if I take the total flux, so the total flux, well, yeah, so the total flux is going to be equal to the total amount of this junk. So all of these vectors going into and out of this surface, which I will call S. So I'll say this is the flux through S. Okay, so now when I split this up, this surface will get split into some piece S. Whoa, don't know what happened there. S2 and S1, right? That my surface is going to split. Then I have a piece which is associated with V1 and a piece which is associated to V2. Oh, Horace, good luck on your QFT oral exam. Be a fun one. Hope it goes well for you. But so once I do this, I split this. So the total flux, say the total flux going out of V1 is equal to the flux going out of S1, right? Just this piece of the surface, the piece of the surface surrounding V1, plus the flux out of V1 through sigma. Right, so it's going to be this piece here plus the piece going through sigma. Just the total flux going out of V1. Now V2, we can do the same thing. And it's going to look very similar. Phi sigma V1. Or, sorry, V2. But putting all this together, I can see that, well, the flux going through S is equal to the flux going through S1 plus the flux going through S2. I'm just splitting up this surface into two pieces, and that's not going to change the total amount of flux going through the surface. But in particular, we can see that if I add these two subvolumes, the flux going out of these two subvolumes, I get, this is equal to phi s, right? So this guy, that's just combining this and this, plus phi through sigma V1, plus phi through sigma V2. But I know that this is true, so these two cancel. And I get that this is just, again, equal to phi total. This might seem obvious, but it's very important to show it explicitly because this means that I can cut up a volume arbitrarily and as long as I sum the fluxes from all of the subvolumes, I still get the total flux. Still get the total flux. So it doesn't matter how I cut this thing up, as long as I add up all of the subvolumes, I still get the same answer. So what we're going to do is we're going to take our original volume, and again, this is going to be quite the test of my drawing capabilities, our original volume V, and we're going to cut it up into tiny little hypercubes. Because remember, we're not actually working with a three-dimensional space, just looks like it. I'm obviously not going to draw all of them, but the idea is something like this, right? We're just going to cut it up into a whole bunch of tiny little cubes, which go all the way through this volume. Okay? In particular, so I'm going to call each one of these dV. So if I blow up this dV, I'm going to draw it as a cube, but remember that this is a 2n dimensional cube. So it's not an actual cube, but my abilities to draw in 2 dimensions are lacking enough. I don't need to try to draw in 2n dimensions. Okay, so this is dV. And in particular, the volume of dV is going to be equal to the side length, which I'll call epsilon. So this is epsilon to the 2n, right? Just the side length raised to the number of dimensions that I have. Okay, so now I need to look at the flux out of this guy. So we'll say that this guy is centered on the phase space point z naught. Then we can look at this, we can look at the flux through just, say, one of the faces. So we'll say this is in the z1 direction. Z1 direction, in which case our normal vector is just going to be z hat 1, right? It's the normal vector pointed perpendicular to this guy. So when I do n hat dot z dot, oh, n hat I zi dot, this is just going to be z1 dot. And let's not forget that this is going to depend on all of our coordinates. Yeah, I'll just call this z sub L. But if I'm just restricting myself to looking at what's happening on this face here, then I'm going to end up fixing where I'm at in the z1 direction. Right, so I'm fixing myself to be at z1 plus epsilon over 2, and then z2, z3, all the way up to z sub 2n. Right? So now when I integrate over ds, you can see this is just integrating over all of the directions which are not z1, right? So this is dz1 or dz2, dz3, all the way up to dz2n. And I'm only going to be integrating over this surface. So I'm going to be going from minus epsilon over 2 to epsilon over 2. In which case, the flux through dz or z1 plus. So this is the plus side of dz1. We still have a negative dz side that we'll look at next. And this is going to be dependent on where we look at originally. This is the integral minus epsilon over 2 dz2, and all of these other integrals are going to be included in this dot dot dot. dz sub 2n, z dot 1, z1 plus epsilon over 2, all the way up to 2n. Okay, so now I'm going to look, so everything is a small variation. Variation around z0I, which means I can expand. I can expand this in epsilon in particular. So I can write, and this is kind of a cheeky way of doing things. In principle, you want to expand the entire integral, but all of the corrections are going to end up being higher order. Z sub 2n. This, I'm just going to expand this very naively. Z dot 1 evaluated at z0 plus epsilon over 2 dz dot dz1 z sub L 0 sub L. So we're just evaluating this derivative at dz0, and this is plus higher orders epsilon square, which I don't really care about. So now I just plug this in, notice that now nothing actually depends on any of these coordinates, right? I'm evaluating everything at a fixed point, so I can just plug this in and do the integrals, which are just each integral is going to give me a factor of epsilon, right? Because I'm just going to be integrating dz from minus epsilon to epsilon over 2, which is epsilon. So in this case, I get something which looks like this. z1 dot plus epsilon over 2 dz dot 1 dz1. Of course, this is evaluated at z0. And I'm going to have 2n minus 1 of these integrals. So this is going to give me epsilon to the 2n minus 1. Whew, okay, so that's one of our faces, one face of our cube. So now let's do the opposite face. Okay. So if we define our z dot vector as, I'll say, it's not always going to be pointed in the positive direction, but we'll just define it so that if we have some n hat pointed out this way, n sub I z sub I dot is going to be negative in this case, n minus here. And you can see this works out because if z dot I is negative, then this gives me a negative value, or it gives me a positive value, sorry. So with that in mind, this whole calculation is gonna be pretty much the exact same, save for two small changes. Namely that I'm gonna be looking at z1 minus epsilon over 2 instead of plus. And then I get an overall minus sign in my flux because of this minus sign here. Okay? So in this case, I get something which, if I have done this all correctly, z1 minus z0l equal to, I get that overall minus sign, z1 dot, and then I'm expanding about minus epsilon over 2, right? Because that's the location of this new surface. dz dot 1, dz1, epsilon to the 2n minus 1. And of course, both of these are plus higher order corrections. So now I'm just going to repeat this. So you see that when I add up the fluxes in the z1 direction, this term and this term are going to cancel, but these two terms are going to add together. So that my total flux in the z1 direction, zl0, is just going to be epsilon to the 2n, dz1 dot dz1. Plus, of course, higher order corrections. But there's nothing really special about the z1 direction, so of course we can just apply this to all of our directions. Right? So that my total flux coming out of this small volume, which I'll call phi dv, centered at dzl0, this is equal to epsilon to the 2n. I get dz dot 1, dz1 plus dz dot 2, dz2 plus dz to n, dz to n, plus, of course, can't forget our higher order corrections. So now I want to make dv completely infinitesimal by taking epsilon to 0. And so you see that this here becomes my infinitesimal volume element. And all of these higher order terms drop out. So phi dv in this case is just equal to, and I'm going to write this as dv dz dot sub I dz sub I. Actually, I want to call this n to sort of stay consistent with what I was doing earlier, where the repeated indices are, of course, summed. We are summing repeated indices in a derivative like this, and n is 1 up to 2n. Okay, so now to get my total flux through this surface, I just add up all of these fluxes, which means I just integrate over all of these little volumes. So I find that phi, the flux out of the total volume, is equal to the integral over the full volume, dz dot n dz n. Okay? But what we found before is that the total flux out of V, out of our volume V, was equal to the total amount of Z, which was going through our surface S, right? This is our Z dot. Sorry, I want to change these to, I know I was using I's before, but originally I was using, I don't think I'll use M's here. But so this, we now have an equality between these two fluxes. These two expressions for the same flux. Now, notice that there was nothing really special about z dot. We never had to really assume, you know, this was a time derivative or anything like that. So this is actually true for any general vector field. And the theorem is this guy. df sub I d I'll keep calling it z sub I, but it doesn't have to be in phase space. It doesn't have to be any. This is just a mathematical relation that is always true for any vector field f. This is true for any vector field f, and in this case it's a function of z. And this is known as Gauss's theorem. Or it's also called the divergence theorem. Very, very important. Shows up everywhere. This is a very, very important relation. And it's actually pretty simple if we think about it. So the left-hand side, as we've already said, this is the amount of F which is flowing through our surface, the surface of our volume, right? Well, the right-hand side is giving us essentially how much F is changing in the direction that it's pointing. So how much it's flowing outwards from a point. So putting these two sides together, we say that the right-hand side tells us the total amount of F which is flowing out of the volume, whereas the left-hand side tells us the total amount of F which is flowing through the surface. So all this is saying, all Gauss's theorem is, right? So this is actually a great way to remember Gauss's theorem if you're having a hard time remembering equations. Just remember that Gauss's theorem just says that whatever flows out of a volume V has to flow through the surface bounding V. That's all Gauss's theorem is saying. And again, this seems very intuitive, but we now have a mathematical proof of it. Yeah, it's very useful when designing electromotors. Yeah, this shows up all the time in electromagnetism in particular. It's one of the reasons why Gauss's law is called Gauss's law, is because of this exact theorem. Okay, but anyway, that's great. We've proven something very general in math, but what does this have to do with phase space? Well, we found before that dv dt is equal to this integral, n sub I, I keep going back to i's, n sub m, z sub m. I like to index I from 1 to n rather than 1 to 2m. But we just found that this can be written as this volume integral. dz dot m dz m. Okay? Where, again, of course, we're summing over indices. But what is this quantity? dz dot sub m dz sub m is equal to dxi plus dp dot I dpi, where now I am indexing m is 1 up to 2n, and I is 1 up to n. But we know what x dot and p dot are from Hamilton's equations. So we can rewrite this as dxi dh dp sub I plus d by dp sub I minus dh dx sub I. But since the x's and p's are independent variables, their derivatives are going to commute with each other, meaning that it doesn't matter the order which I take the derivatives in. I can take the derivative of h with respect to x and then p, or vice versa. So this, I'll get something like d2h dxi dpi minus d2h dxi dpi, which is 0. So what we've shown is that dv dt equal to this integral dz sub m is equal to 0, which means that the total volume in phase space never changes. Never changes. It's a constant. It's a complete constant. So when I was showing this animation earlier, let me pull it up again, and the stretching and squeezing that we saw, it looks complicated, whatever, but it is absolutely a constant. The volume is never changing in this. In this case, the volume is an area, but the area of this shape is never changing. And that's just what we've proven here. And this result is known as Liouville's theorem. Those look like two V's. Liouville's theorem. And it just states that the volume occupied in phase space is a constant of motion. There's another way of saying this. So we know that paths can't cross in phase space. We've already shown that is the case. Which means that if I have some boundary, which is just a continuous set of points, and I have all of the points inside, as this thing evolves, points can never leave this blob, right? Or else the path of this point would have to intersect the path of, say, this point, right? So I don't know, this might evolve into something here, which looks different, but we know has the same volume. And something that we now know is that this volume, this has the exact same number of points. Right, because if points left or came in, we would have paths crossing in phase space, which we can't have. But if the volume doesn't change, and the total number of points doesn't change, then that means that the density of points also doesn't change. So this is another statement of Liouville's theorem, just that the density of the points in a chunk of phase space is never going to change, which is, it's a very cool thing, right? It's a very cool thing, and already discussed how this might be a very useful idea in something like statistical mechanics, where you're considering just tons and tons and tons of initial points and looking at how things might evolve in the future. But we'll see shortly how it can be applied in a context outside of that. So I'm gonna pause here and see if there's any questions, comments, whatever. If you think Liouville's theorem is super awesome like I do, feel free to let me know. I have to agree with Narf that Phase Space Hypercube is an excellent band name. And that, yeah, it's not surprising to see Gauss's name show up again. I was a absolute genius. Incredible. The contributions he made to math and physics. What exactly do I mean by point here? Yeah, so I mean, we can sort of think of, instead of having a continuous blob, right, just have a cloud of starting points for our system, right? Remember that before, when we have these phase space plots, we start at a point, and then that point evolves to some different point later, and that evolution is described by Hamilton's equations. So basically what I'm saying here is that if I just consider that, so consider just, instead of a continuous blob, I have just a cloud of these points, which are each individual systems evolving through phase space, then that number of points is not going to change in this cloud. I mean, essentially, that's sort of obvious, right? Because this is never going to hit a hit a point where it disappears or pops out of nothing, right? It can't, because that would essentially require two paths to converge like this. And then two could become on here. Exactly, just like the particles in a fluid. And so then, if I want to actually describe it as a fluid, I can take the continuum limit where I have an infinite number of these particles, in which case I no longer want to talk about the number of particles. I want to talk about the density of the particle. And so since we have the number of particles is going to be the same, the volume that the particles occupy is going to be the same, then I know that the density is always going to be the same. And that is exactly how incompressible fluid behaves. So this is what I was saying earlier, that exactly, it's an incompressible fluid. We can sort of think of these blobs in phase space as an incompressible fluid, which is very cool because, you know, there's tons of work which has described the dynamics of incompressible fluids. So there we go. We have a whole chunk of machinery which we can now use. We're not going to be doing that today, I will warn you. We're not going to be applying any of that stuff today, but okay, I think I want to get on to the last result. And this is going back to actually doing physics. This has been a lot of math, a lot of proofs. And we're going to be talking about the double pendulum. Everybody loves the double pendulum. It's a really cool system to look at. And if you haven't seen anything about the double pendulum before, you're in for a bit of a treat, in my opinion. So the double pendulum is pretty simple. Well, the setup is simple, I should say. The actual dynamics is very, very complicated. So we're going to take one pendulum, give it a mass m1, and to that, we're going to attach a second pendulum. We'll give a mass m2. Just for sort of simplicity's sake, we're going to say both of these pendulums have a length L. Okay. So the last piece is that there's a force of gravity pulling down on these with constant g, and we're going to fix them here. We can write down the Hamiltonian in Cartesian coordinates. I'll call this x1, y1, x2, y2, and then p sub x1, p sub y1, p sub x2, p sub y2. This is 1 over 2m1, p sub x1 squared, p sub x2 squared. And I know it's kind of dumb to write this in Cartesian coordinates, but I just kind of want to do this to illustrate a point. This should not be x2, be y1. 1 p sub y1 squared. And then I need the potential energy, which is just m1 gy1. So the height of this thing plus m2 gy2, height of the second one. Yeah, so Narf, you're exactly right. So this means that if we only consider the evolution of the surface of the blob, we can still be sure that all of the phase space vectors that make up the volume is still contained by that surface. Exactly, yes. Everything, yeah, like I said, nothing's gonna leave, come in, appear out of nowhere, disappear. any of that, if we just look at the surface, the evolution of the surface, that means that we're looking at essentially the evolution of the whole thing, the whole bulk, you might say. Okay. So this is particularly simple, but we have to remember that these pendulums we're going to assume are rigid, so their motion is going to be constrained, and their motion is going to be constrained to circles centered around their anchor points. Right, so the M1 is going to rotate around this anchor point, and M2 is going to rotate about this anchor point. So we have to write down some constraint equations. The first one is straightforward. This is just the equation of a circle centered at the origin with radius L. The second one's a little bit harder to see, but it just comes from the fact that we are offsetting the origin of the M2 circle by the location of M1, right? So the x direction center of the M2 circle is given by x1, and same for y1. So this is just given by this equation, x2 minus x1 squared plus y2 minus y1 squared. So this is just the equation of a circle offset from the origin by the point x1, x2, or x1, y1. So, how many degrees of freedom do we have? Well, we have two particles in 2 dimensions. So on the surface, it seems like we have 4. But remember, we also have 2 constraint equations. And if you remember, our total number of degrees of freedom is going to be equal to we can sort of say the number of particles times the number of dimensions minus the number of constraints. So in this case, we actually only have 2 degrees of freedom, right? So we have 2 particles moving in 2 dimensions. That gives us 4 minus our 2 constraint equations. We have 2 degrees of freedom. So it's probably going to be a lot more convenient to only have 2 coordinates, right? Rather than having to deal with these stupid constraint equations, let's just come up with some coordinates which satisfy those constraint equations just trivially, that we define the coordinates so that they do satisfy the constraints. And that way we don't ever have to worry about the constraint equations again. So 2 pretty obvious choices, sort of, up to sines, cosines, and sines. We have 2 which satisfy the first equation very well. Sine phi y1 equals minus L cosine phi. So this is just defining, I'll redraw the picture. Actually, I'll write down the second constraint equation first. X2 minus x1 is going to be L sine theta. And then y2 minus y1 is minus L cosine theta. And this just corresponds to this picture here, where I have, oh, this is ugly, but I have this situation where this guy is phi, and this guy is theta. Okay. So I can be a little bit better with the second constraint. And I'm going to actually just rewrite them. Basically just substitute in these guys. so that I can write it in just in terms of x2 and y2. So I do this, and I do L sine phi. Y1 is minus L cosine phi. X2 is L times sine theta plus sine phi. And y2 minus L cosine theta plus cosine phi. So these are my new coordinates. Now, okay, this is where we would typically go ahead and, we just find the elements of G inverse, ... plug it into the Hamiltonian, all that. At this point, we have to be a bit careful. If we tried to just do this, we would get the wrong answer. And the reason is that this coordinate transformation is not invertible. What does that mean? It means that there's not a unique way I can write phi and theta in terms of x1, x2, y1, and y2. I've already defined x1, y1, x2, and y2 in terms of theta and phi, but I can't really go in the opposite direction. As you see, I have to satisfy 4 equations for 2 unknowns. I just can't really do that. So in this case, I have to do what I can with the transformations I'm given. Which means we first have to find the elements of G, and then find G's inverse by normal means. So if you like a more mathy way of saying this, it basically means that for this transformation, your Jacobian matrix is not invertible. And that just comes from essentially the fact that it's not a square matrix. For those that are interested in that, that's sort of beside the point, but yeah. So we've done this a million times, right? I mean, I know that I can write, I can start in Cartesian coordinates and write G as dxk, dqi, dxk, dqj, which means I just need to take derivatives of this coordinate transformation. Again, we've seen this time and time again, so I'm not really going to bother you with that, unless people really want to see it. I'm just going to write it down. So you get g phi is equal to m1 L squared, m2 L squared, g theta phi is equal to m2 L squared, cosine theta minus phi, and then g theta theta is equal to m2 L squared. And now we use this to find G inverse. By using GIK, G inverse Kj should be equal to the Kronecker delta. And this just gives us a set of three independent equations, which we can solve for the 3 independent elements of G inverse. When we do that, we get something that looks like G sub phi inverse is m2 over m1, m2, L squared plus, and I mean, this is absolutely horrendous. I'm warning you now. Theta minus phi. G theta phi inverse is m2 cosine theta minus phi over m1 m2 L squared plus 2L squared sine squared theta minus phi. And then g theta theta is still not really that much better. Over m1 plus m2 squared L squared sine squared theta minus phi. Great, and so then we plug this into the Hamiltonian, right? Our Hamiltonian is going to be p sub I, g inverse I, j, p sub j, plus our potential, which I can write. I'm not going to bother writing the kinetic term. It's not enlightening in the slightest. Actually, this guy should have a minus sign. There, yeah. m1 plus m2 gl cosine phi minus m2 gl cosine theta. So, I mean, this is absolutely horrible. The Hamiltonian's horrible. The equations of motion are horrible. We're never going to be able to solve this analytically. So we're not going to try this. But the good news is we can solve it numerically. And so we can solve it numerically, look at the evolution in both physical space as well as in phase space. So kind of the plan of action is we're going to first solve numerically, of course, Hamilton's equations of motion. And we're going to look at 3 different systems. For all three systems, m1 equals m2. This is all just for numerical convenience, essentially. Pi at t equals 0 is pi over 2. And p theta at t equals 0 is equal to p phi at t equals 0, which is equal to 0. But we're going to run 3 different situations. The first being theta at t equals 0 is equal to pi over 2 minus 0.001. The second is theta at t equals 0 is equal to pi over 2. And the third is theta at t equals 0 is equal to pi over 2 plus 0.001. Now, these are tiny offsets in our initial conditions, right? Our initial conditions are almost exactly the same. So what we might expect to happen is that, there's basically no distinction between these systems. Let them evolve. Yeah, they're going to be tiny, tiny differences, but, the differences are just going to be the differences in the initial conditions, and, it'll be kind of boring because you won't have any huge variations this close together. So let's go ahead and see what happens when we do this. So this is our old phase space. So now, come here, and we look at these. And it starts out, these all evolve very, very similarly. They're very close to each other. And then sort of all of a sudden, they all just completely go crazy. And now, after a few seconds, it's just a few seconds that it takes for this to happen, these 3 systems look completely different. Completely different systems. Even though we barely offset their initial conditions. So we can go through this again. So you see that they look nothing alike. You would have no idea that we started their initial conditions so close together. And this is the idea at the core of what's known as chaos theory. And basically, the whole idea is that a teeny tiny change in the initial conditions has drastic effects later on. So this concept is typically referred to as the butterfly effect, right? Where a tiny, tiny change, something like the flap of a butterfly's wings, the air from the flap of a butterfly's wings, can cause the system to end up evolving completely differently later on in time. I think it was Euler, if I'm not mistaken, who also defined it as the exact present determines the exact future, right? Each of these is the evolution of a single point through phase space. It's exactly deterministic, right? If we know the exact state of the system at any one time, we know the exact state of the system at any other time. But what Euler said was that the exact present determines the exact future, but the approximate present does not determine the approximate future. And that's sort of the idea behind chaos theory, is that if I get close to the right answer in the present, and I can try to extrapolate that to the future, but good luck, right? Yeah, so as Robert's saying, why weather forecasts are so difficult? Weather's an extremely complicated system. So trying to determine it is incredibly challenging because there's so many, because it is chaotic. But I on that note, I shouldn't misspeak, because in mathematics, chaos does not mean complicated in the same way that complex does not mean difficult, right? So complex number is a very simple thing. In the same way, this chaotic system is very simple. It's just a 2-degree of freedom system. It's still chaotic, but we can have a many degree of freedom system that isn't going to be chaotic, right? So complicated does not mean chaotic. Chaotic does not mean complicated necessarily. But that's sort of the idea. So let's try to think about this in terms of our phase space idea, right? So when we say two systems are very different in the context of phase space, what does that mean? Well, with this evolution, you can see that these points, again, I'm going to draw it as 2-dimensional. Remember, it's really 4-dimensional. All 3 of these points start very close together in phase space, and actually I'll just offset them by a tiny amount here. Teeny tiny offsets in phase space initially. And each one of these, they're going to evolve in some way, however it may evolve. And we saw that initially, all 3 of them evolved very close to each other. But then pretty soon, their evolution diverged. And similar for this guy here, right? So by saying that the points, or that the systems are very different in a later time, what we're essentially saying is that the points end up at very different points in phase space. We evolve it, and these points end up very far apart in phase space after some given amount of time. Now this might raise some flags, because so say I take some blob, again, in phase space, here, and I start it in this state. Well, then I know that any 2 points which are very close together are going to end up, after a long period of time, very far apart, which means that this blob is going to get smeared out in phase space. It's essentially going to spread out and fill up all of energetic phase space. all of the energetically available phase space. Sorry. But that should raise red flags, because we just definitively proved, that any system which satisfies Hamilton's equations of motion, the volume in phase space never changes. So how can this ever be possible? How can we ever have a chaotic system like this, where the volume has to spread out, right? The two systems arbitrarily close together have to spread out to be very far apart for a chaotic system. So how can this ever be the case? And actually, I'm going to take a quick pause here and see if people have answers. I need a drink of water, and I'm curious to see what people think in chat, because this is a very interesting idea. And so let me know what you guys think. How to sort of resolve this. Does this apply backwards? Does the approximate present determine the approximate past? Oh yeah, for sure. Well, okay, the approximate present determine the approximate past? No. Not for a chaotic system. For a non-chaotic system, certainly. But, I mean, that's sort of the beautiful thing about these systems, is a lot of times you can run it backwards in time and you'll see a very similar thing happen, right? And you'll get something like this if I were to run this backwards in time. Right, and these paths will also end up diverging, but they'll stay close, sort of bunched up together as I run time backwards as well. But yeah. Okay. So this interesting problem, right? We have this very interesting problem where it seems like we've broken our own theorem that we've applied. Now, as it turns out, what ends up happening with this is that this is going to evolve, and it's going to end up evolving, and it's going to very, very intricately fold in on itself. Like, sort of like this. Without... This is a very, very neatly ordered folding. Not so neat in actuality, but you'll see that if I do this folding right, Narf has the exact correct answer. It's fractal phase space. When I do this folding right, it's going to fold in on itself and keep folding and folding and folding. I never have to increase the volume, but I take up more and more space. And so this is why, and granted, I will preface I will preface this with, I am certainly not an expert in chaotic systems. So this is my limited knowledge of chaos theory. But these are the sort of ideas that show up frequently. And so this is why fractals in particular are very commonly studied in chaos theory, and for chaotic physics in general. This is one of the reasons, because you get fractals have this great way of folding in on themselves in order to take up as much volume as they possibly can without getting infinite volumes or anything like that themselves. So with that said, I want to show you guys the evolution of phase space. Actually, before I do that, I want to sort of, again, preface what you're about to see. So what I'm going to show you is the evolution of, it's this system, but with a sort of blob of theta values. Actually, theta and p theta values. So I fix p phi at 0, and I fix phi at 0. But I'm going to draw a blob in p theta and theta. And we're going to track the phase space evolution of sort of a cross-section of phase space. So remember, phase space in this case is 4-dimensional. We're just going to track what is an initial, it's an initial circle in theta p theta. But we're only ever going to look at the theta p theta plane. So what you'll see is this blob will look like it's crossing over itself. But remember, we still have 2 other dimensions that this thing can move in. And it might also look like it's changing volume, which in this case it is, but that volume is being sort of pushed into the phi p phi plane as well. So sort of keep all of that in mind when watching this. And also, at some point, this thing stretches out to the point where the initial circle, I think, had 10,000 points on it. And the points on the surface end up getting far enough apart to where, you get artifacting, where, what should be a smooth line just looks like a straight line. So those are my 2 things prefacing this, in which case I will sit back and let you watch what I personally think is one of the more beautiful animations that I've made. So you can watch this thing sort of spread out and start to fold in on itself as it begins to take up more and more of the phase space. And you can see exactly like what we were expecting. This thing is going to be taking up, in principle, there should be a modulus in 2 pi on theta, but that would just add another layer of confusion, but whatever. So yeah, you see that these points are getting very, very far apart from each other. Where it started out as just a tiny little circle, folds in on itself, and spreads out. And like I said, I think this is probably one of the more beautiful animations that at least I've made. Yeah. So this is the idea of chaos. Yeah. Through the full blob, there's going to be gaps between the final conditions. I think so, yeah. But yeah, so this is yeah, keeping in mind this is just a subspace of the full, it's sort of a cross section of a blob in phase space, but yeah. This is again, this is the idea of chaos, or another definition of a chaotic system, that some volume in phase space will eventually evolve to take up the full energetically available phase space. Yeah, I agree that it looks very, very cool. I think this is excellent. But yeah, I think this is kind of where I want to wrap up with things. If anybody has any questions, feel free to let me know. Be more than happy to answer anything. Give it a few minutes, can watch the animation go. please, but. Yeah, Luis, I'll be posting this. I mean, it'll go up on my channel right after this, so you'll be able to watch it through whenever. And if you have questions going through it, I try to respond to comments and stuff. So feel free to leave a comment if you want to watch it at your convenience. So. Yeah, I always think these phase space evolution plots are very cool. Yeah, I think I agree with you, Robert. This would be a cool cool screensaver. The only issue is that it's my computer wasn't happy about solving the Hamiltonian equations for this many points. So it might be might be a little computationally intensive for a screensaver. I don't know. Yeah, so Narf, this is a good question. So you said earlier that the phase space vectors aren't quote unquote real vectors because their components transform differently. Can't you just write the transformation matrix to say that they transform in the correct way? So when we call something a vector, we mean something very specific in its transformation properties. And so this is something that comes up in general relativity a lot in particular, but so if you remember, talked about a while ago, a tensor is something that transforms like a tensor, right? Everyone hates when people say that, but that's probably the easiest way to define what a tensor is, as long as you give the tensor transformation. A true vector, an actual vector, transforms like as we call it, a rank 1 tensor, a one-dimensional tensor. So it's not just writing down a transformation matrix. That transformation matrix has to be a very specific form for it to be considered an actual vector. So if you want the more the better way of saying things, the q's, the coordinates, transform as vectors, or I always get it mixed up. I believe contravariant vectors, if you like, while as the p's transform as dual vectors, or I believe it's covariant. I think I have the covariant and contravariant. I always get those two mixed up. So you're sort of mixing covariant and contravariant vectors into Z. So it itself is neither one, if that makes sense. So that's why I said it's not a real vector. It's not truly a vector. Yeah. Oh, the phase space is the phase space a vector space plus its dual space. Oh, I'd have to think about that. Yeah, I don't know if if I'm confident enough to answer that. right now. I'd have to give it some thought. Or given definition of plus. Yeah, I hesitantly say that it's the direct product space, but I'm not 100% confident in that. So I definitely don't quote me on that. But if I had to venture a guess at this point, you could probably define it as the direct product space. But again, don't take that to heart. I don't know that for sure. Yes, and now everyone has an excellent quote from me that is probably wrong. But yeah, and I'm sure that people in the chat or the comments later on will be have much more expertise in defining vector spaces. And so, of course, feel free to chime in on that. But yeah, I think this might be a good point to wrap things up. I appreciate everyone for coming. Hope you enjoyed it. Like I said, I think this is pretty cool. I might leave links to these animations in the code that I use to generate them in the comments of the video. So, or maybe I'll if people want them, maybe I'll post like a community post with them or something like that. I don't know. Haven't quite decided yet, but yeah. If people want to play around with it and all that, then feel free to let me know if that's something you're interested in. But I think that I think I'll wrap it up here. So thanks everyone for the support, and coming and the engagement and all that good stuff. I will see you on the next one.